Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at how geologists explore for mineral deposits. So when a geologist goes into an area looking for a mineral deposit, the chances of you walking into that area and instantly finding what you're looking for are practically zero. So the vast majority of deposits are going to be concealed in some way. There could be sediment on top of them, rock on top of them, there could be plant life on top of them. And so what geologists are going to have to do is they're going to have to use indicators to try and guide you towards the mineralization. So you're going to be looking at the rocks and you're going to be using that information to say, right, I think the mineralization is probably located in this area. You can also use other methods like geophysics in order to identify possible targets, which you can then go and investigate in greater detail. Okay, so we're going to begin by looking at how geologists do field work to locate potential mineral deposits. So for every type of mineral deposits, geologists will produce what's referred to as a genesis model. So that simply says, right, if I'm looking for this type of deposit, what conditions does this type of deposit form under? And so it's going to tell geologists things like, what type of rocks are associated with this type of mineralization? What kind of tectonic setting will I find it in? Convergent or divergent? Is it associated with any kind of structures like folds, faults, joints? Is there something to do with the fluid chemistry? So, for instance, is this type of deposit formed by fluids which are given off by magmas, or is it formed by circulating seawater, or is it formed by fluids which are produced during the liquefaction of sedimentary rocks? We are also going to have in that genesis model things like what type of alteration minerals are produced by the mineralizing process. So, for instance, as a hydrothermal fluid passes through an area, it's going to change the minerals that it comes in contact with. And so we can look for those alteration minerals. Then we're also going to look at the genesis model and we're going to say, right, what are the indicator minerals? Because sometimes in order to actually find what you're looking for, you can't see the mineral of interest. So you have to use an associated mineral to actually say, right, that's the mineralization. So if you think back to low-grade gold deposits, those are associated with gold contained within pyrite and arsenopyrite. So the gold is so small you can't see it, but you can see the pyrite crystals and the arsenopyrite crystals. And so that's going to give you an idea about, right, this is probably where the mineralization is. And of course, you're also going to be looking for the minerals of economic interest. So if you're lucky, you will actually be able to see the minerals you're looking for. And so your genesis model is going to contain all of this information. And so as a geologist, you're going to say, right, this is what I'm looking for this type of mineral deposit. Where in the world can I find rocks that have experienced these kinds of conditions? And so that's how you're going to begin your investigation. So once you've picked your target area based on the genesis model for the type of mineralization you're looking for, you're then going to go in as an exploration geologist and you're going to begin reviewing things such as geologic maps, and you're going to try and locate areas with the potential to host deposit your minerals of interest. So once you've identified your area and you said, right, this area had the correct conditions, then you're going to go in finer detail with geologic maps and you're going to say, right, this northwest corner looks particularly good. And so I think we're going to start there. So when you have selected your location, you're then going to send geologists in and they are going to begin to map the rocks to understand the history and the development of the area. So if we just have a look at the pictures here, one of the things that geologists are going to look for when they are investigating or trying to locate mineral deposits, we're going to look for alteration. And so you can see that this particular rock, you can see it's full of fractures, and these fractures have clearly been exploited by hydrothermal fluids, and it's resulted in the formation of this greenish mineral. This is an alteration mineral caused by the hydrothermal fluid. And so we can use this kind of information to say, right, a hydrothermal fluid has definitely passed through this body of rock. And from the fact that there is a lot of alteration, it would suggest that there has been a lot of hydrothermal fluid passing through this rock. I therefore think that this rock is a good potential target to have to host mineralization. And so then you'll take a sample of this rock and you'll send it to a lab to be assayed to work out what the chemistry of the rock is. So these are the basic steps that a geologist is going to take when looking for a mineral deposit. So once you've actually gotten into your area, what are the more fine-grained techniques that you're going to be using? So most mineral deposits are not visible at the surface. So geologists will have to start looking for indicators of those mineral deposits. So the first thing is, of course, alteration, which I was just speaking about a second ago. And so some types of mineralization are associated with very specific types of alteration. You see that type of alteration, you know there's a very good chance you have that type of mineral deposit. There will also be changes in the intensity of the alteration associated with mineralization. So typically, when you have things like hydrothermal fluid flow, there will be a feature which will be exploited by the hydrothermal fluid. So if we look back at this diagram here, let's say for argument's sake, this fault plane here is being exploited by hydrothermal fluids. And so obviously the strongest alteration is going to be located to the place where we have the fluids flowing, so near the fault. As you move away from the fault, the intensity of that alteration is going to decrease. And so what we can do is we can say, right, here's some alteration. Is it intense? Grade it from 1 to 10. If I go this way, does the alteration get more intense? Yes. I'm going to keep going that way because as it keeps getting more intense, that's probably going to lead me towards the actual mineralization itself, which is what I'm looking for. So alteration's very, very important for geologists. We're obviously also going to be looking for structures because we want to try and find fluid pathways. So we're going to be looking for faults, we're going to be looking for folds, we're going to be looking for just areas of rock that have been tectonically deformed, because that's going to offer the kind of conduits through which magmas and through which hydrothermal fluids can move. So the next thing we're going to look at is rock chemistry. So sometimes two rocks can look exactly the same. And a good example of this would be something like a basalt from Hawaii and a basalt from the seafloor, the Mid-Atlantic Ridge. Now, they're going to look exactly the same. However, there will be very small differences in the chemistry between these two types of basalt. The one from Hawaii is formed due to a hotspot. The one at the Mid-Atlantic Ridge is formed due to a divergent plate boundary. This is actually going to produce slightly different chemistries in your basalt. So certain rock chemistries are more likely to yield mineralization. So for instance, there are certain types of granite and certain types of andesite, or should I say, granodiorite, that are more likely to produce mineralization. And one of the ways you can see whether they are that correct type of intrusion is by looking at the chemistry of the rock. And so certain rock chemistries are more likely to yield mineralization, and so you're naturally going to focus on that type of intrusion. You're also going to look for missing elements. So if you take a sample of your rock and you suddenly go, well, hold on a minute, according to the scientific research, there should be, 0.5% copper in this rock, but there isn't 0.5% copper, it's gone. Well, that's going to make you instantly think, where has that copper gone? And that's going to tell you, once again, there was probably a hydrothermal fluid moving around in the area which has dissolved the copper and taken it somewhere else. And so rock chemistry is very, very important to geologists because it helps us to identify potential targets, and it also helps us to identify areas where we are missing important elements. And that shows us, right, this area has been scavenged. Where have those elements gone? Geologists will also then use soil and water chemistry to try and find the mineral deposits. So typically, your mineral deposit's going to be buried. So there's going to be a layer of soil above it. And that soil consists of a mixture of different materials. It consists of air, water, organic material, and most importantly, pieces of rock from the rock below. And so what geologists will do is they will take a sample of the soil and they will send it to a lab to be assayed to get the chemistry, and they will look for the presence of certain elements. So they might, if you're looking for copper, they might look for how much copper is in this soil. And if there's an anomalously high amount, well, that's going to suggest, right, underneath this soil, there is quite possibly copper mineralization. In the case of water chemistry, what you'll do is you will take water samples up a river valley. So you'll start at the foot of the river and you'll start working uphill, taking water samples as you go up. And then you'll send those water samples for assay. And if you happen to have a source of mineralization and the water is passing by it, as you move towards the point of mineralization where the water becomes contaminated by that element because of the mineralization, you will be able to measure a change in the chemistry of the water as you get closer to your mineralization. And so the soil and water chemistries are often used to identify what are referred to as pathfinder elements. And these pathfinder elements could be the element of interest. So it could be copper, lead, or zinc, or it could be an element that is associated with the element of interest. So in the case of gold, a classic pathfinder mineral would be arsenic. And so you're going to look for these elements in your data set, and you're going to be looking at it and you're going to say, right, I can see if I look at these water samples, as I go upstream, I can see the amount of copper in the water increasing. That tells me that we have, we are more likely to have mineralization going upstream on this river. And the final thing that we're going to be keep an eye out for is the presence of key minerals and, more importantly, their alteration products. So sometimes if you are super lucky, you will actually be able to walk around and you'll find an outcrop and the mineral of interest will be right there in front of you. But that's very unlikely. So if you think about something like a porphyry copper deposit, the ore itself will typically only contain about 0.5% copper sulfide mineral. And typically those copper sulfide minerals will be disseminated. So they'll be there as a fine mist of copper sulfide minerals spread throughout your rock. So they're not going to be easy to see. However, when your copper sulfide minerals are exposed to the atmosphere, they are going to begin to break down. And they are going to start forming a range of different minerals, including copper carbonate. And so as your copper sulfides break down, you'll start forming these brightly colored copper carbonate minerals. And so as a geologist, you'll go walking around and you'll say, oh, I see that very bright green-blue color over there. Well, that's a really strong indicator that there is copper mineralization in that rock. You will also look for other things such as this rusty red color. This is referred to as gossan. And this is the result of iron sulfide minerals, so pyrite, breaking down in contact with oxygen and water. And so the presence of this gossan tells you that, right, although it's now been destroyed, once upon a time, there were sulfides here. And so that tells me there are sulfides in this area somewhere. I need to go hunting for them. They're somewhere nearby. So there's lots of information that a geologist will be collecting as they walk around in the field to try and guide them towards their mineral deposit. So next, if you are a geologist working in an area, and if you are lucky enough to have sufficient money, you will also employ geophysical surveys to help you find targets. So in terms of the final thing that geologists will look for, we're going to look at plate tectonics and the settings which are associated with each type of mineral deposit. And so these will be part of the Genesis model. So for instance, we know that porphyry coppers are typically associated with convergent plate boundaries. We know that volcanogenic massive sulfide deposits are typically associated with divergent plate boundaries. So one of the things we're going to look for is we're going to look for the correct type of tectonic regime for the mineral deposit that we are looking for. So your plate tectonic setting is going to control things like rock types, sediment present, the structures that form, and the types of magma produced. So they're going to have a very big influence on whether you will find the type of mineral deposit you are looking for. So a good example of this is, of course, porphyry coppers, which are associated with convergent plate boundary. So even if the event that formed the porphyry copper occurred millions of years ago, the deposit may still survive. So the classic example of this is the Olatolgoi deposit in Mongolia. This is a porphyry copper, and it formed during the Upper Devonian, so about 372 million years ago, as part of what's referred to as the Central Asian Orogenic Belt, which was a sequence of collisions that helped to build the continent of Asia. So even though the mountains that were formed by this orogeny are now completely gone, they've been eroded away, the porphyry copper system that was formed as part of that convergent plate boundary is still there. And so geologists went into that area, they looked at the rocks and they said, right, based on what I can see, the evidence shows me that these rocks were once part of a convergent plate boundary. And once they had that information, they then released the geologists and they said, right, look for indicators of mineralization. And so geologists went out and they started looking for indicators of mineralization in the surrounding rock. And they ended up finding an absolutely massive porphyry copper deposit. Okay, so let's get on to the use of geophysics in order to help geologists locate mineral deposits. So a range of geophysical techniques can be used in exploration. And these four are just a few of the possible options. But we're going to look at magnetic surveys, gravity surveys, resistivity, and something referred to as induced polarization. So in the case of magnetic surveys, what they do is they focus on the presence of magnetic minerals in the subsurface geology. So certain minerals like magnetite, hematite, pyrrhotite, ilmenite, and chromite have a slight magnetic signature. And so the presence of them in your rock is going to affect the magnetic signal of your area. And these minerals are common in igneous and metamorphic rock types and certain types of mineral deposit. So if we look at our schematic diagram here, you will see here is a graph showing essentially the magnetism of your area. And you can see your magnetism is starting quite low because you've got a sequence of sedimentary rocks. You will then see over here, your magnetism has increased because you have igneous rocks. Igneous rocks will often contain minerals like magnetite and ilmenite. So your igneous rock is going to naturally be slightly more magnetic than your pile of sedimentary rocks over here. So that's why the magnetic signature is slightly higher. But then if you look at your graph, you will notice you have this noticeable peak right here where the magnetic signature is noticeably higher than even the intrusion. And this is a really strong indicator that you have a buildup of some kind of magnetic mineral in that area. Now, it doesn't tell you whether that mineral is going to be associated with something economic that you can mine, but it just says, right, something is located right here that's giving off a magnetic signature. This could be the mineralization you are looking for. Now, the other type of survey the second type of survey we're looking at are gravity surveys. And gravity surveys measure how subsurface rocks cause changes in the strength of the Earth's gravity. So a gravity survey will reflect changes in the density between rock types. So gravity surveys look for highs and lows. So highs are associated with dense rocks like igneous and metamorphic rocks or mineralization, whereas lows are associated with less dense rocks like brecciated rocks and hydrothermally altered rock. So as a geologist, if you have a gravity survey done, you're going to be looking for rocks which have a high signal and rocks which have a low signal, because If they have a high, that could suggest maybe you have mineralization there. If there is a low, it could suggest maybe a hydrothermal fluid has passed through this area, and that's going to help to guide me towards my mineralization. So if we look at these two surveys over here, you can see here we have a gravity survey of New Jersey. Now, this is quite a coarse survey, so you're covering quite a large area. But straight away, you can see based on the gravity survey, you clearly have rocks here and here that have a higher gravity signature, and you obviously have rocks over here that have a lower gravity signature. And so that would suggest straight away that this area here, which is giving the reds, purples, and pinks, is probably a mixture of igneous and metamorphic rocks, compared to this area up here that has the cooler blues. That's probably sedimentary rock. So although you can't get super fine detail out of this survey, straight away you're saying, right, this area is probably mostly igneous metamorphic, this area is probably mostly sedimentary, and you can also see that there is a distinctive curve to this particular feature here. And then you're going to think to yourself, right, what could possibly be producing a curve like this, which is, it's pretty big, bearing in mind the size of the survey here. And so instantly, as a geologist, I'm thinking that could possibly be some kind of orogenic event, some kind of mountain building process in the past. Now, if we look at the magnetic survey here, what we're doing is we're looking for rocks that contain these magnetic minerals. So where we get highs, we are probably looking at igneous and metamorphic rocks, and where we get lows, we are probably looking at sedimentary. So once again, all of these reds, pinks, and purples, those are probably going to be igneous or metamorphic rocks, whereas all these blues, those are more likely to be areas that have sedimentary rocks in them. But once again, you can see there is a very obvious feature coming through this data from New Jersey once again. So straight away, that's making me think, what could possibly form this type of feature? And so once again, I'm kind of instantly drawn to the idea that this could be an indicator of some kind of orogenic event having happened. And so this would make me think as a mineral geologist, okay, I have indicators that there could have been a convergent plate boundary here at some point. That increases the chance that this area could be prospective for porphyry copper deposits. So another type of survey that can be used is called a resistivity survey. And a resistivity survey essentially uses electrodes in the ground to see how easily a rock will conduct an electrical current. So if your rock contains metallic minerals, so sulfides or oxides, tungstates, native elements, those minerals are really good at conducting an electric current. So the resistivity will be quite low because the electric current will flow through those rocks very, very easily. Compare that to a regular rock like a granite. Well, that's made up of minerals that do not conduct electricity very well. And so that will have a high resistivity. So resistivity surveys are really good for locating portions of an area where you are more likely to have minerals that will conduct electricity. And so those areas are more likely to be your mineral deposit. The final method that you can use is called induced polarization. And what this does is, just like resistivity, it pushes an electric current into a layer of rock, but then you turn off the power. And then what you're measuring is you're measuring the chargeability of the rock. And this is essentially how well does the rock actually store the electric charge. So what geophysicists will do is they can measure how quickly the electricity dissipates, how quickly it disappears. And so rocks with a high chargeability may contain polarizable minerals like sulfides or clays. And so what you want is you want a high induced polarization signal, because that's going to suggest, right, there could be sulfides in this rock, because this rock is really good at holding an electrical charge. induced polarization might sound a lot like resistivity, but it does have one big advantage, and that is that induced polarization is really good at detecting disseminated mineralization. So it's really helpful when looking for porphyry coppers, because even if your sulfide mineralization is spread out as this mist of fine copper sulfide crystals throughout your volume of rock, an induced polarization study will look at that rock, it will fire the electric current into it, and it will say, right, this rock is actually quite chargeable, even though I can't really see the mineralization that easily. That would suggest that this rock contains a lot of very fine disseminated mineralization. And so geologists will use geophysical methods, and they will combine them with field work and sampling, and that will allow them to begin to focus in on areas that are more likely to host their mineral deposit of choice. So, like I mentioned previously, geologists will also use soil and water sampling, but they will also use other techniques as well, which I'm not going to go into detail about, things like GIS, and this uses satellite images to analyze an area. And so what you can do is you can use these satellite images, and you can actually play with the wavelengths of light, and you can use that to select certain wavelengths which may be associated with your type of mineralization. You can also have geologists that go out into the area and they look at the plant life associated with the area, because there are rare types of plants which are associated with certain types of mineral deposits in some parts of the world. And so once again, as a geologist, if you can go out and you look for the correct plant, that's going to say, right, there is a good chance that there is mineralization in the soil beneath this plant. Okay, so once we actually find our mineral deposit and we work out, right, is there ore here? Can we economically extract this? And you make a decision and you say, yes, we can economically extract it. You're now at the point where you need to work out how you're actually going to do that. So if a deposit is located close enough to the surface, you're going to go with open pit mining. It's the easiest, safest, and cheapest method of mining. You're just simply going to strip off the stuff above your deposit that you don't want, and then you're just going to dig up your deposit to extract the ore. Now, the decision to build an open pit mine is controlled by what's called the strip ratio. And for most open pit mines, the strip ratio is going to be 2:1 to 4:1. So for every 1 ton of ore, you will be removing 2 tons of rock, which is essentially waste rock, in order to get to your mineral deposit. So you don't really want to be removing more than 4 tons of rock for every 1 ton of ore. So once you have located your ore and you've essentially accessed it, you are then going to blast your ore. And this is going to involve drilling holes in your rock face. You're going to load explosives, and then you're going to essentially cause a coal explosion. You're going to blow up an area of your mine, and then you're going to come in and you are going to use excavators to obviously pick up the pieces of rock and put them into dump trucks to be taken away. And of course, these open pit mines lead to very significant environmental disruption, because you are stripping off the topsoil, you are exposing the rock underneath, and you're essentially creating a very, very large void. And yes, some of the waste material from the mine will then be used to fill the open pit back in once you finish mining. But you are still taking rock out, so no matter how hard you try, you are still putting back less material than was there originally. So you can never completely recreate the topography of an area after you have mined it using open pit mining methods. Now, in the event that your mineralization is not accessible to open pit mining, you're going to have to go to underground mining. Now, straight away, underground mining is more expensive, it's way more costly, it's way more dangerous, and so straight away, the grade of your ore needs to be higher because you need to be earning more money in order to pay for the construction of this more expensive underground mine. So underground, you are going to locate your mineralization and you're going to blast it. And you are then going to haul the rock that you produce to the surface using either trains or a conveyor belt or mine shafts or dump trucks, depending on how your mine is designed. Now, as mentioned, underground mines are way more expensive than open pit mines. And the method will change depending on whether the ore occurs as a single vein, thick seam, or dissemination. So there are several different types of underground mining. If your mineralization occurs as just a single vein, you're just going to follow that vein. If it occurs as a disseminated style of mineralization, you're going to try and take everything, because anything that can have mineralization in it is going to be worth taking. And so in the case of a single vein, you're going to be very selective in your mining process. Whereas in the case of disseminated mineralization, you're going to go for a bulk mining process. You're just going to take everything. So the style of underground mining you're going to use is going to be controlled by the style of mineralization. Now, once you've extracted your ore, it will initially be crushed to produce chunks between 1 and 10 centimeters in size. And at this point, if the minerals within your ore can be dissolved by acid, so in the case of porphyry coppers, that's possible, you can then take this crushed rock and you can put it onto what's called a leach pad. And on the leach pad, you will pile up your ore and then you will pour a solution of acidic water over your pile of ore. And as that acidic water passes through your pile of ore, it will dissolve the copper mineralization and you will collect the liquid at the bottom that's both a mixture of your acidic water and now copper mineralization with dissolved in that water. And so leach pads are a very efficient way of collecting mineralization. However, they do have problems. The first one is they're very, very big and they are cheap to do, yes, but they are best used for low grade, high tonnage ores. So providing you have the correct type of ore, great. If you don't have the correct type of ore, leaching like this using this heap leach method is not going to be particularly effective. Another issue with heap leaching is that it requires very large areas to build the pads, and the rate of metal recovery is very, very slow because you're constantly pouring this slightly acidic water over the ore, and this is a process that happens over a period of weeks. So it's quite a slow recovery of metal. Now, in the event that heap leaching will not work, you're going to need to go to another method to actually extract the mineral of interest. So when you need to move to the other method, you're going to move to something which is referred to as flotation or froth flotation. And in order to do this, you're going to need to take your pieces of crushed rock and you're going to need to pulp them down in a mill to produce a fine powder with particles between particles around 75 microns in size. So that's 0.075 millimeters in size. So you've really turned your rock to a very fine powder. Now, once you have your pulverized ore, you're going to mix it with water and it's going to produce something called a slurry. And the slurry will then be sent for flotation. So in your flotation tanks, you're going to mix the slurry with something called a collector, the type of chemical that will focus just on your mineral of interest. It's specifically designed to latch onto the mineral of interest. And you're also going to start pumping air bubbles through this mixture of slurry and the chemical collector. And the bubbles are very important because the collector chemical is going to make your mineral of interest stick to the outside of the bubbles. And so that as the bubbles rise up through the slurry, it's going to take your mineralization of interest with it. And then what happens is you just let the bubbles naturally fall over the side of the tank, and you collect your now mineralization rich liquid down here, and then you can send it for processing. So the recovered material, which falls over the side, is then dried and it's sold as concentrate, which can then be put into smelters to actually get the metal out. So froth flotation is arguably the most common way of extracting metals from ore. So you can also use some other methods. So for some copper and uranium mines, they will employ an in situ leach process. We've already discussed this in earlier videos. So this is essentially where you drill a borehole and you pump down a mixture of water and special chemicals, and they will dissolve your mineral of interest from the rock underground, and then you can pump that solution back to the surface and send it for processing. And this method is very cost efficient. It's less environmentally damaging than building a mine, but it does require the layer of rock you're targeting to have a high permeability, because obviously you need your fluid to flow through the rock in order to dissolve the minerals of interest. All right. Thank you for watching, everybody.